Good morning, everyone. This is Philip Griffiths in Miami, and it's a pleasure to welcome all of you to this morning's lecture in the MSAC Consortium Distinguished Lecture Series. Our speaker is María Esteban, who studies nonlinear PDE, applications to physics, quantum chemistry, and fluid structure interaction. María was an invited speaker at the 2018 ICM. In 2019, she received the Siam Prize for Distinguished Service to the Profession and became a member of the Academia Europaea. In 2020, she received the French Academy of Sciences Prize Jean-Louis Lyon. Dr. Esteban was president of the International Congress for Industrial and Applied Mathematics for the 2015-2019 term, and was president of the Society of Applied Mathematics Applied in Industry from 2009 to 2012. It's a great pleasure to welcome her for this morning's lecture and on functional inequalities and improvements, stability. María, welcome.
Thank you very much for the nice introduction, and thank you very much for you for being there and for the invitation to give these two talks. Okay, so I'm going to speak about functional inequalities and stability for them. I'm going to speak about several works that I've done along the years in this. It's a long program that I have been developing mainly with my two collaborators, Jean Dolbeau from my university in Paris and Michael Loss from Georgia Tech in Atlanta. I will speak about some of the results will be done also with other people, other collaborators, but Dolbeau and Loss are my main collaborators all along this program. I will be speaking about several things. First, I will start about speaking a little bit about symmetry and symmetry breaking in PDEs and further than PDEs. Then, in a very general and informal way, I introduce what the functional inequalities are and what they are good for. Then I will speak more concretely about the use of linear or nonlinear flows to prove functional inequalities and describe the optimizers and the best constants. And that I will give examples on the flat space, but also manifolds. Finally, I will arrive to speak about improving optimalist inequalities. This sounds a little bit strange because if inequality is optimal, you shouldn't be able to improve it, but you will see in which sense. I will speak about it, and then I will describe what stability is and what people are doing about it nowadays. In the meantime, I will touch upon several things, for example, applications of these functional inequalities to obtain spectral estimates on compact and non-compact manifolds, and this is important in mathematical physics and also in differential geometry. I will speak in the second talk a little bit about interpolation inequalities with magnetic fields and other methods. Okay, so I will also give a list of open problems in the second talk. Okay, so I will start with, symmetry and symmetry breaking. So in a very informal way, I will say that the issue of symmetry and symmetry breaking is fundamental in all areas of science, not only mathematics, but also in physics, a lot in chemistry, biology, etc. Symmetry is often assimilated to order and beauty. We like to see these fractals and these crystals and these beautiful drawings. Okay, so it's assimilated really to order and beauty. And symmetries are fundamental properties of the laws of physics. In particular, symmetries impose constraints on modeling phenomena, and at a more basic level, they serve as criteria of classification for solutions, models, etc. The first person who probably spoke about symmetry in a scientific manner was Pierre Curie, who stated his principle in 94. This is called Curie's principle. And so he was working on crystallography, so it makes sense to be speaking about symmetry in that framework. And what this principle says is that the symmetries of the causes are to be found in the effects. What it means is that you have a problem that is invariant by a group of symmetries, and then the solutions of that model should have the same symmetries. So the causes are the model, the effects are the solutions, what you see. Well, Curie himself saw before he died that this principle had some counterexamples. There are cases, and we are going to talk about it a little bit later, in which the problem that you are looking at has a lot of symmetries, and there are solutions for it that don't have the same symmetries. And this is something which is very important, and this is called symmetry breaking. And symmetry breaking is the source also of many interesting phenomena, such as phase transitions and complex dynamics in physics, instabilities, segregation, self-organization. So I could say that both properties, symmetry and symmetry breaking, are present in many phenomena in nature, in physics, for example, in mathematics also, and both are equally important. And even talking to physicists some years ago about these questions of symmetry breaking, they told me, you know, symmetry breaking appears much more often in real problems than symmetry. So symmetry is almost an exception. And symmetry breaking is very important to justify and motivate and understand many interesting phenomena in nature. Now, knowing a priori, if you are mathematicians, we are mathematicians, knowing a priori the symmetry properties of solutions of, for example, PDEs or other kinds of problems, biaxial problems, for example, which are invariant under some symmetry group, is of fundamental importance. So knowing a priori, you are looking for a solution, whether it has this or that symmetry is important. Why? Well, it's important by itself, of course. It's important for us to understand the qualitative properties of the solutions of the problems we're studying. But also, you want, for example, to do some numerical computations, and this is important if we are working on applications, physics, chemistry, geology, etc. When you want to compute the solution of a problem, it's important to know about the symmetry properties, because if you know that the solution is going to enjoy some symmetry, then there will be simplifications in your code. There will be many fewer degrees of freedom. For example, imagine that we are looking at a problem in 3D, and the problem is a complicated equation in 3D, and you want to compute it numerically. You will have to spend some time and energy to solve it. But if you know a priori that the solutions you are looking for are radially symmetric, the equations suddenly will not be a PDE in 3D, they will be an ODE in 1D, and that is much easier to compute, okay? So knowing about the symmetry properties of solutions a priori is very important to simplify your life, for example, when you have to run numerical computations. Now, let's give you a little example of, a little counter example to Curie's principle. Imagine that we have in 2D a potential like this. This is which is called a Mexican hat potential, V. And you see this potential is radially symmetric. You see the level lines here on the right. They are perfect circles, okay? So this potential is radially symmetric. And we are going to use it in a PDE that will appear in the next slide. So here we have a PDE, which you see as an elliptic PDE simple minus Laplacian U plus the potential V times U minus F prime of U equal 0, where F is a nice nonlinear equation function. And then look at the solution of this equation. So I plotted it as solution of this equation, and you see that it has a little bit the same structure as the potential V. It looks a little bit like a Mexican hat again. So it has a maximum, a local maximum here at the origin, and then the minimum is achieved in a circle around it. I mean, and here are the level lines of the solution. So you see the level lines of the solution are perfect circles. So this solution has the same kind of symmetries as the potential V that we had in the equation. Okay? Now, so this seems to satisfy Curie's principle. The causes here are the potential, they are radially symmetric, and the effects, the solution, is radially symmetric. But if I compute further, I can find other solutions of the same equation, which is like this, which is not radially symmetric. You see here, it has a little bump on the side, okay? And if you look at the level lines, you will see that the level lines are not perfect circles, because here on the right, we see this little hill that appears on the side, okay? So you see that we have an equation that is invariant by rotation, so you should expect that the solutions would be also invariant by rotation, but it is not the case. Some of them are invariant by rotation, and some of them, like this one, are not radially symmetric. Okay, they are not invariant by rotation. So this is a counterexample, for example, to Curie's principle, a simple one. So this is complicated because you have the same equation and you have symmetric and non-symmetric solutions. Then you see that it's going to be difficult to see in which cases you have symmetric solutions, in which case you don't have them. Okay, so you have to be able to classify them. And what is still more striking is that in general, you are looking at physical problems, often the most favorable solutions that minimize some kind of energy, that correspond to more stable solutions, like this one, for example, they are not radially symmetric. You see symmetry breaking. So the more stability you look for your system, the more the equation is going to try to break the symmetry. So this is something that is complicated in applications, and we will see some applications later about this. Okay, I just wanted to give you an example of the complications you can encounter. Now let's go to the second topic, which is the main topic actually of these talks, which are functional inequalities. So what is functional inequality? Functional inequality, in a very general manner, I can describe an expression like this. We are working in a functional space X, function space that can be, I don't know, a Sobolev space, it can be an LT space, it can be a functional space X. And we are looking at functions V, which are in that functional space. And a functional inequality will be an expression like this, inequality like this, that says that the functional f of V, x will be the variable in the space in which we are working, maybe some derivatives. This functional will be controlled by a constant c times another functional of what? Of B, derivatives of B, and maybe higher derivatives. And in many of the existing functional inequalities I will be describing later, we will see that indeed in the right-hand side, we have higher derivatives than in the left-hand side. So of course, I will give examples in which I will say what is F, what is Z, etc. But I just wanted to give you the expression of a functional inequality in a very general and abstract manner, okay? And the best constant C will be the smallest one for which we have this inequality for every V in the space X. Okay, functional inequalities like these, concrete ones, play an important role in obtaining a priori estimates for solution of PDE. So PDE people use functional inequalities all the time. They are also important in analyzing long-time behavior of solutions of evolution problems. You are looking at the heat equation, or you are looking at the wave equation, the Schrödinger equation, evolution ones, depending on time. Then studying the long-time behavior of the solutions of those equations will be done very often with the help of well-adapted ad hoc functional inequalities. Also recently, these kind of functional inequalities have been used very much to describe the blow-up profile of finite time blow-up. For example, there's been a lot of activity in the PDE community to try to understand possible blow-up in finite time for solutions of the nonlinear heat equation or Schrödinger equation in physics. And so in order to describe how the blow-up takes place, what is the profile of the blow-up, these kind of inequalities play also a very important role. They are very helpful. And also I will explain a little bit later, some 2 or 3 slides later, that inequalities of this kind are also important, for example, in a very different topic in quantum mechanics, to prove spectral estimates for Schrödinger operators. Also in differential geometry, we find functional inequalities very often, okay? So now more concretely, many examples of functional inequalities, for example, very old ones like Hardy inequality, of Helder inequality, of Poincaré inequality. I think that everybody listening to me know them, Jensen inequality, okay? But then more recent ones, for example, that maybe they are not so known outside some math communities, for example, Nash or Sobolev inequalities, Gagliardo-Niederberg, Log-Sobolev, Karparelli-Niederberg, etc., etc. There are many, many, many functional inequalities. And I could say that the set of functional inequalities is a very important toolbox in analysis, in mathematical physics, in differential geometry, and in probability. Probably these 4 communities are the ones that are more interested in understanding various functional inequalities, in understanding the values of the best constant, in understanding the optimizers of the inequality. Optimizers or extremal functions are the functions V for which we have equality in the inequality, okay? The ones that just are sharply, we have the sharp inequality with equality. So there are many, many, many inequalities examples in different contexts. So the important questions when you have a precise inequality is to understand whether the best constant is achieved or not. What is the value of the best constant? And if yes, if it's achieved, you want to know what the optimal functions are, how they look like, what are the qualitative properties, whether they have, for example, symmetry properties, because as we will see later, if you know that they satisfy symmetry properties, it will be easier to compute the value of the best constant, etc., etc. Okay, so these are general questions. So I'm speaking in a very general and informal way. Now, let me present to you another slide, still in the very informal and general setup, to show to you, to explain a little bit the link between interpolation inequalities, functional inequalities, and variational problems and partial differential equations, why there is a strong relation between these topics that a priori maybe you don't see. The first link is very easy to see, is if you have an inequality here with a best constant C for the inequality in some space X, it's easy to see, very easy, it's really almost trivial to prove that this inequality is totally equivalent to a minimization problem, which consists in writing that 1 over the best constant, C, is equal to the infimum in the space X of a functional, which is actually the right-hand side of the inequality divided by the left-hand side. So this is really almost trivial to be proved, okay? So you have an inequality and you call C the best constant, 1 over C will be the minimum or the infimum of the functional, which is defined like this. So there is a very natural relation between inequalities and minimization problems. And because of that, in my talks, I will sometimes speak about extremal functions or optimal functions of the inequalities, or I will say minimizers, because it's the same, you know, being a minimizer here, V is a minimizer for this minimization problem, if and only if V is extremal functions of this inequality for which we have equality, okay? So these are equivalent problems, good. Now, of course, it's good because it tells us that we can use variational techniques, minimization techniques, to study functional inequalities. Now, there is another relation that is important, which is the following. If we have B hat, or B bar, which is a minimizer for this minimization problem, and which is equivalent, is an extremal function for the inequality 1, then it is almost trivial if G and F have enough regularity properties. I'm not going to go into the details. It will be easy to prove that V bar will satisfy a partial differential equation that can be written like this. The differential of G equal to some constant mu differential of F, whereby differential of J, I denote that the functional derivative of J for any functional G, okay, J. So this tells us that when we have an optimal function, an extremal function for inequality, or what is equivalent, a minimizer for a minimization problem, if we have enough regularity in the functionals, then this function will satisfy a PDE or an ODE, okay? So we see immediately a relation between functional inequalities and PDEs or ODEs. Now, this equation, which is satisfied by the minimizers of this problem, is not equivalent to the other ones. So what we have is if B bar is a solution of 1 or of 2, then it will satisfy 3. But the opposite is not true. There will be possible solutions of the equation 3, which are not minimizers of this or extremal functions of this, because when you have an equation, you can have solutions which correspond to all the critical points of this variational problem. They can be saddle points, maxima, etc., etc. They don't need to be the infimum of the function. Okay, but we see a relation between inequalities and PDEs. Let me just end this slide by saying that this equation 3 is called the Euler-Lagrange equation associated with the minimization problem 2. Okay, and the constant mu, which appears in the equation, is the associated Lagrange multiplier. Okay, so this is just to explain the relation between functional inequalities and PDE theory. Now, let me show to you, before I start really talking about real inequalities, let me explain to you another important link, and it's the link between functional inequalities and quantum mechanics, operator theory. So I'm going to explain to you in a very, I hope, simple manner, how studying these functional inequalities is actually, they are a very good tool to obtain spectral estimates for Schrödinger operators in quantum mechanics. So this is why in mathematical physics, in quantum mechanics, people are very interested about the study of functional inequalities. So let me explain that with a little example. Suppose that we have a second order elliptic operator L. It can be minus Laplacian, an operator which is non-negative, for example, minus Laplacian. And we are going to consider the minimization problem described like this, minus Laplacian UU, which means actually by integration by parts, the integral of gradient U squared, plus alpha times UU, so the integral UU is just the integral of U squared. And then in the denominator, I write the integral in the space, I mean, in the domain in which we are working, of UP to the integral to the 2 over P, where P is any number between 2 and 2 star. And this 2 star is an important number in when we study functional inequalities, which is called Sobolev critical exponent, and its value is 2D. This is the dimension of the space in which we are working, divided by D minus 2. For simplicity, assume that D is larger than 3 or 3, and so we don't have any singularities in this exponent, okay? So this inequality is a very simple inequality that we can consider in domains of, for example, it can be a manifold, it can be a domain of RD, whatever, you know, and it can be a bounded domain, it can be an unbounded domain, it can be, I'm just speaking in a very, very loose way for the moment. Okay, so if we look at this minimization problem, I'm going to call the value of the minimum, I'm going to call mu of alpha. And alpha refers to the constant that is multiplying here, UU, the scalar product in the 2 of U and U, so it's the integral of U squared. Okay, so this is this parameter alpha that appears in the value of the infimum. So this problem is equivalent to this inequality. This is trivial, as we said before. Now, consider the function, look at the inverse function. So you see when alpha, I mean, mu of alpha is an increasing function of alpha. You see it immediately because alpha is multiplying a positive thing and everything is positive otherwise in the expressions, okay? So mu is an increasing function of lambda. So we can consider the inverse, alpha of mu, okay? And so this is just the inverse function, okay? So they are scalar functions and it is the inverse. And now let me look at the following thing. Let me consider any potential V, any function V in LQ. Q is related to P, the P which appears in the inequality by this relation, U1 over Q plus 2 over P equal to 1. And then let's call mu the LQ norm of the positive part of this function V. Okay, this is just notation. Good. Now let's look at this expression, red expression here, L minus V multiplied by U times U and divided by UU. Okay, this is scalar product in L2, for example. So what is this? This is just what is called the Rayleigh quotient of the operator L minus V. If, for example, you have a matrix, instead of having an operator, you have a matrix A, AU multiplied by U divided by UU is just the Rayleigh quotient associated to the matrix A. And it's the thing you want to minimize when you want to look at the minimal eigenvalue of a matrix. You have a matrix A, you look at AUU divided by UU, and you minimize that to get the first eigenvalue. Well, it's the same for operators. So now we are doing this for the operator L minus V. L was the elliptic operator I considered here, and V is the potential in LQ that I just chose here. Okay, so we look at this quotient. Then we can see that this quotient is bounded below by LUU, that's the same, we don't change. And then instead of B, we write the positive part of P, okay? And this is trivial because the positive part is larger than the function itself. And then we use Holder estimate, a very trivial Holder estimate, to say that this guy, this V plus UU, is bounded above, but with the minus sign is bounded below by this expression. And this expression is just the integral of UP to the 2 over P, and mu, which is just the LQ norm of P plus. This is just Holder inequality. So these are very, very trivial inequalities. But now when we look at this expression here, this quotient here, which is a lower bound for the initial quotient, we remember that mu is the norm, LQ norm of V plus, and we remember this inequality that we had above. And in this inequality, we see expressions like LUU minus mu to the, if we pass this to the left-hand side, and we pass the alpha UU to the right-hand side, by using this inequality that we had, we can say that the numerator is bounded below by minus alpha UU. But minus alpha UU divided by UU is just minus alpha. Okay, so by using this inequality here in a very trivial way, we see that the Rayleigh quotient of the operator L minus V is bounded below by minus alpha of mu. Alpha, remember, is the inverse function of mu. Okay, so now we see that we have a chain of inequalities. In the right-hand side, we have a number. In the left-hand side, we have something that depends on U. So the right-hand side doesn't depend on U. So we can take the minimum in all these inequalities, and what we'll get is that the minimum of the Rayleigh quotient, which is the first eigenvalue of the operator L minus V, is bounded below by minus alpha of mu. And mu, remember, is the LQ norm of P plus. So what have we proved? By using, in a very simple way, this functional inequality, we have proved that the first eigenvalue of this Schrödinger operator is bounded below by this number. And this for every V in LQ. So this is a very strong spectral result for a large family, very large family of Schrödinger operators. And it comes for free if you know this functional inequality. So this is why people in quantum mechanics, in mathematical physics, are interested in these inequalities, because they get interesting spectral estimates for the ground state energy of their problem, for the first eigenvalue of the Schrödinger operators they are interested in. And we have also optimality results. Here we have extremal function for which we have equality. Here we have equality also, etc. So there is a very strong link between these spectral estimates and inequalities. Okay, so this is another motivation to study functional inequalities. And now, after all this introduction, let me go to real inequalities. I will present in this talk and in the next one 2 or 3 inequalities in which I will explain the results one can obtain, the applications, the methods, etc., etc. So let's look now at a very, very simple inequality, which is Gagliardo-Nirenberg-Sobolev inequalities in the sphere. So what is this inequality? This inequality is the following. You are in the unit sphere in dimension d plus 1, so it's the d-dimensional sphere, and you consider this inequality. This inequality is written for every u in the space H1, maybe for people who are not in analysis. H1 is the Sobolev space, which consists of the functions that are square integrable and whose gradient, first derivatives, are also square integrable. Okay, so we look at this space. So we consider any function u in this space, finding the sphere ST, and we take the standard uniform probability measure on the sphere. Okay, and then we say we write this inequality, which is the following. We say that when we know that the L2 norm square of the gradient of u is finite, we know that this quantity here is also finite, bounded by this number. So what we know is that the L2 norm square of the gradient of u controls by behind the constant d divided by p minus 2 and the difference, or the LP norm square of u minus the L2 norm square of u. Okay, so this inequality was well known for many years, but without knowing many details about it. What was known is that there existed some constant c for which this was true, and it was known, that was the only thing you knew, that there was some constant c for which you had this inequality. And recently, more recently, let's say, it has been proved that the best constant is this guy here, and that the only extremal functions, the only functions u for which you have equality here, are the constants, constant functions on the sphere. Okay, so this has been proved more recently. I'm going to give some names soon. And just to give you something to hold to, just say that these inequalities on the sphere, you take a stereographic projection in the particular case when P is equal to 2 star, this critical Sobolev exponent, this inequality is just equivalent to the very famous Sobolev inequality on the flat space RD. The Sobolev inequality is very, very famous in PD theory and in differential geometry. Okay, so this inequality in the flat space is equivalent to this inequality on the unit sphere by using stereographic projection in the case when P is equal to 2 star. Okay, now, who are the names attached to the proof of this optimal inequality? The names are the following. The first people who proved this inequality with the best constant d over p minus 2 were 2 French analysts, Bidot and Veron, and they proved that in 91, this was one of the results contained in a paper published in Invenciones, and they used the PD methods to prove this result. 2 years later, there is another proof of the same result in another paper published in Invenciones again, written by Beckner, who used totally different methods to prove the same thing, the fact that this is the best constant, d divided by p minus 2, and that the only optimizers for the inequality are the constant functions. Beckner proved these inequalities 2 years later, and by the unfairness of life and of our topic, and it happens often, these inequalities are known in the literature as Beckner inequalities, even if he was not the first one proving them. Okay. Anyway, that's not a very important thing, it's just an anecdote. But you look further in the literature and you look to articles in probability, you see that there is an article in 85 earlier by two French probabilists, Bakry and Emery, who proved the inequality. But I didn't quote them first because actually they didn't prove the inequality in all generality. They proved the inequality by using a very different method that is called Carré-Duchamp method, which is related to some probability methods. And they proved the inequalities for p less than 2 sharp. And this 2 sharp is a number that is strictly less than 2 star. So they prove the inequality for a smaller class of p's, okay? So the result is less strong than the optimal result that was proved later by Vidal-Veron and Beckler, okay? But even so, you see, there are people in different communities interested at the same time in the 80s about this kind of functional inequalities. We have people in probability, people in PD, people in analysis, okay? So this was really a very trendy topic at the time. And even if Bakry-Emery's result is not the optimal one, I will explain the proof because the proof is very easy to understand. So it's easy for a talk like this. And also because the method they use can be used in many other inequalities. So I find that the method is much more flexible, robust, and exportable to other situations. So I have chosen to explain to you the main ideas behind the proof of Bakry and Emery because it's really, the ideas are really easy to understand and to explain to a general audience. So what Bakry-Emery wanted was to prove this inequality here with the best constant d divided by p minus 2. And what they did is to write this inequality, instead of writing it for you, they wrote it for rho, which is just the absolute value of u to the p, okay? So you look at the inequality satisfied by rho is this one, is the absolute equivalent when you say that rho is just u to the p, okay? Now, so what they want is to prove the following. They want to prove that I is larger than dE when I is defined as the integral of this term. So this is what you find here in the left-hand side of the inequality. And E of rho is what you find in the right-hand side of the inequality without the d here, okay? So it's 1 divided by p minus 2, the difference of these two integrals. So they wanted to prove that I is larger than d times E and that the d is the best constant, okay? Now, how they came around it? What they did was to consider a Brownian motion. So they considered something that is linked to the linear heat equation. So they considered the linear heat equation for rho, where the linear heat equation is defined on the sphere. So this Laplacian is not the usual Laplacian in the flat space. This is the Laplace-Beltrami operator on the unit sphere. Okay, so this is the linear heat equation, very well known. And then with some initial datum. And so it's very easy to see, at least formally, that if you look at the evolution along the heat equation of the integral of rho, the mass of rho, you can see that this is equal to 0 because of the equation. And you can see also that if p is less than 2 sharp, this number that I defined in the previous slide, you can see that the derivative of E, this guy who is here, derivative of E is minus 2 times I, the guy who is here, and that the derivative of I is less than minus 2 times d times I. So they prove these very simple inequalities or equalities for p less than 2 sharp. And with this, the proof becomes very easy, you are going to see. Because the goal was to prove that I minus d times E is larger than 0 for every rho 0. So what they do, Bakry-Emery, is to consider any p less than 2 sharp or equal. They consider the linear heat equation with initial datum rho 0. And then they use the previous inequalities and they see that the derivative of with respect to t along the heat flow of the expression I minus dE is less than 2 times minus d plus t times I using the previous inequalities, which is 0. So what they see is that this quantity, I minus dE, is decreasing along the flow. Okay, it's decaying. Good. is decaying. At the same time, it's not difficult to prove that for general initial datum, rho 0 in general functional spaces, rho converges to a constant. The solution of the heat equation converges to a constant as t goes to infinity, and that the limit when t goes to infinity of the expression I minus dE is equal to 0. So you have quantity that is decaying towards 0. So you decay towards 0, the only possibility is that time t equal to 0, you were either positive or 0, because in order to decay to 0, you have to start at some positive or null level, okay? So what they prove by this simple argument is that at the initial time, they had to be at 0 or above 0 in order to be able to decay towards 0. So you see the idea is very simple. Of course, you have to do some functional analysis to prove this rigorously, but the idea is really very, very simple. And analyzing also how negative the derivative is, they can prove also that the only extremals, the only functions rho 0 for which you have equality here are the constant functions. So this is the proof, the idea of Bakry-Emery, that for me is really a great result. I mean, great idea, very simple, but really great. And as you see later, very easy to export to other situations, very flexible and robust method. Now, the question, of course, and the question was posed very often by Bakry himself. I talked to him several times, and he was almost angry with him himself, saying, but why we can't apply our method for p's larger than 2 sharp? Why we can't? If we know that Bidot, Veron, and Beckner proved the result for p up to 2 star, why we can't do it? And he was almost like nervous about it. Why? And then in 2017, with Dolbeau and Loss, we have explained to them, to Bakry in particular, why they couldn't use the method, because it's not usable. Because what we have proved is that for p between 2 star, 2 sharp, and 2 star, then we can find a counterexample. We can find a function rho 0, so that you look at the heat equation with initial datum rho 0, you look at the derivative of this quantity, and you see that the derivative is strictly positive already at t equal to 0. So the method of Bakry-Emery was based on the decay of this quantity. And we see here that if p is larger than 2 sharp, this quantity is not decaying, is increasing actually, okay? So we explained in particular to Bakry why their method couldn't work for p larger than 2 sharp. It's not that they were bad mathematicians not being able to apply, it's that it couldn't be applied. And actually it was very lucky because we could publish this result in a paper dedicated to the 60th birthday of Bakry, so that was nice. Okay, so now what happens for p larger than 2 sharp? What we have proved in the same paper is that you can extend actually the idea of Bakry-Emery to prove the result in the optimal case. And what is the idea? The idea is to consider heat equations that are not nonlinear. You see, we consider, instead of the linear heat equation, we consider derivative of rho with respect to t equal to the Laplacian of rho m, where m is different from 1. Okay, so we by introducing this equation, which is called actually fast diffusion equation, is like a nonlinear heat equation. Let's say we can then use the idea of Bakry-Emery of trying to prove that the quantity I minus dE is decaying along the flow, but now it's decaying along the nonlinear flow. And by using this nonlinear flow, we can extend the idea of Bakry-Emery to cover the optimal result and reach p equal to 2 star. Okay, so we did that in 2017. And of course, going from linear heat equation to nonlinear heat equation, the idea is the same, but the computations are much more involved, but the idea is more or less the same. Okay, so we really stick to this idea of flow, using a flow to prove the inequality. Flow in the sense of evolution equation. Okay, now in a work that we did also with Dolbeau, Loss, and Kowalczyk, we studied a little bit more in detail this inequality, and we saw that, of course, we proved that the quantity I minus d is decaying, but we can prove more in detail about how decaying it is. What is the thing you get, the negative thing you have here? We try to use it to get more information. So we don't want only to use the fact that this derivative is negative or zero. We want to see how negative it is. And by using some inequalities and some easy inequalities, we can see that putting everything together, looking at what this term, this derivative is, etc., we can derive a nonlinear inequality for the functional E that appears here in the DE, okay? So we can derive a nonlinear differential inequality for E, second order differential inequality, that we can study. We can solve, not exactly, but almost. And then we can see that using it, we can prove that I is larger than D times the LP norm squared times phi, some function phi, something that we know exactly how it looks like. In particular, this function phi is larger than E, okay? Phi of E is larger than E, but is strictly larger than E when E is not zero. So what we do is to reprove the inequality that I is larger than DE, but actually we prove that it's strictly larger than DE when E is not equal to zero. And equal to zero means that we are looking at constant functions. So we are improving the inequality when we are away from the extremal functions. When we have a function U, which is not extremal, for which we don't have equality, actually we can measure how positive the inequality will be. And so what we can do is to estimate from below how positive I minus DE is when U is not extremal function. For U, extremal function, I minus DE is equal to zero. But when U is not a constant function, it's not extremal function, we can improve the inequality and we can give a lower estimate, which is strictly positive for non-extremal functions. Okay, so we did that in this work with Kowalczyk, Dolbeau, and Loss, and we come maybe to the end of my talk now. I will introduce this topic of stability. What is stability for inequality? Stability is a notion that is quite studied these days, nowadays, in the PD and in all this community interested in functional inequalities, also in probability. What you want, or what people want, is how well can one measure the distance to the optimizers in a given inequality. So you are extremal functions for the inequality, you have the inequality exactly, okay? But if you are not exactly in extremal functions, how well you can use the inequality to estimate the distance of the function, which is not extremal, to the set of the optimizers. So can one prove that if the function almost attains equality in the optimal inequality, then it is close to one of the optimizers or not? This is a priori not trivial, and the answer is not a priori yes. Okay. So people are very interested to understand this because this measures a little bit the stability of the functional inequality when you get away from the manifold of extremal functions. For example, more in detail, you have an inequality like this, field F larger than C times E, okay, in some space Y, and you denote for Y by Y0 the set of optimizers for this inequality. So Y0 is the set of optimizers for which you have equality here. This is in general for many of the inequalities a manifold. And what you want to do is whether you are able to say that the difference of F minus C is bounded below by some constant time the distance of function U to the manifold of the optimizers, to some P, etc. So this is the question of stability. And what you want is to know what distance you can put here. You want to know what P are you going to put here. You want to measure this constant to know if it's very large, very small, etc., etc. And so this question of stability is a difficult question. I will speak about it in my next talk. It's a very trendy question nowadays. Many people are working in this area nowadays to try to understand for different inequalities, what can you say about the stability of the inequality? How well you can measure the distance of any function to the set of optimizers by looking at how positive the inequality is. Okay, and with this, I will just finish. I finish my time by just giving an example. I will discuss it more in the next talk. The first result in this direction in the flat space was given in a paper by Bianchi and Knell in 91. That is very, very, very quoted. There are many references. You look at MathSciNet. They prove that for the Sobolev inequality, when you look at the difference of the two terms in the Sobolev inequality, they found that the difference is bounded from below by a constant c times the infimum of the distance of the function f to one of the optimizers of the Sobolev inequality. But the problem of this result is that they were unable to measure how big the constant c was. Okay, so I finish with that. Sorry, I'm a little bit late, and I will continue discussing stability, what can be done, what can't be done, etc., in my next talk. So thank you very much for your attention.
Okay, thank you, Maria, for a very interesting and very clear talk. And if anyone has any questions or comments, we would welcome them. In the result you had a few slides back, you had, I think, some phrase, a cleverly chosen, I think it was a phi naught, and
yeah,
and well chosen. What does that mean? Is it easy to say how you choose a well chosen?
Not really. I mean, yeah, I mean, we decided to look at this nonlinear equation. And when you look at the nonlinear equation, you see the set of good functions for this equation, and when they are not good for when you take m equal to 1. Okay, you compare the two equations. And then you see that since the functions initial data that are good for this nonlinear equation are not good for the other one, and that's how you find the counterexample. So it was it's not easy to guess this function rho zero. It was really found through the study of the nonlinear problem.
So you can't do what you want by just, the m is not stable. You can't move it a little bit or anything like that.
Yeah, actually, we're looking at other inequalities at the time, and we understood that linear flows, like the ones used by Bakry-Emery, were very nice, but that they were not. That in many cases you needed to go to nonlinear flows. So we're working in another inequality actually, and we understood that, and then we came back to this one, saying what could work here. And then we looked at this in this nonlinear. We saw which kind of m we needed here, and then we understood, but very indirectly, that we had a counterexample for the other one. So it was not our aim to find the counterexample. It was our aim to just use the nonlinear flow. But doing that, we understood that we had a counterexample for Bakry-Emery with a linear heat equation.
Okay, thank you. Other questions or comments? Look forward to the next talk. And again, thank you very much. And I guess we'll join you again on Wednesday.
Okay, thank you very much
Yep.
for your attention.